In the previous section, we calculated pH and concentration of H3O+, and we used the Ka to do that. Or we were given the pH and we used it to calculate the Ka. It turns out that there's actually another type of calculation you can do that involves the exact same variables, if you will, and that is percent ionization. So the percent ionization is the concentration of H3O+ over the concentration of HA. So when the acid reacts with water, okay, it's going to form H3O+, and in this case Cn- because the acid is HCN. Percent ionization is the percentage of this that turns into this. So instead of looking at pH or Ka like we did in the previous examples, in this example we're simply calculating the percent ionization. It's basically the same thing, you just do a slightly different math at the end. But I still think it's worthwhile to do one example. So as usual, I'm going to switch over to the camera in order to do the example. So let's read this. It says, what is the percent ionization of a 0.0225 molar HCN solution? And then it tells us the Ka of HCN is 4.9 times 10 to the minus 10. So in this question, you see that we have HCN aqueous plus water yields H3O plus Cn minus. And as I just said a minute ago, what we're essentially looking for is the ratio between this and this. This is on the top and this is on the bottom. The greater the percent ionization, the greater the strength of the acid, if you will. But in this case, we're just basically looking for the same variables. So we again need an equilibrium table, just like in the previous section. We have, again, everything that's aqueous in our ice table. I called it an equilibrium table a second ago. I probably should have called it an ice table. All right, and we have everything that's aqueous in it. So if we look here, the HCN concentration, well, that's given to us as 0.0225 molar. The initial concentration of H3O plus and Cn minus are both 0, just like in previous examples. How much of this are we going to lose? We don't know. And how much of this are we going to gain? We don't know. But we do know the stoichiometric relationship between those things. And if you'll notice here, they're all 1 to 1. So for every X of H3O plus that we get, we don't know, we're going to get the same X of Cn minus, and we're going to lose the same X of HCN because one HCN breaks up to form one of these and one of these, if you will. So we know the relationship stoichiometrically, but we don't know the actual value. For the equilibrium, we're going to get 0.0225 minus X. We're going to ignore that X as we have in previous examples. So 0.0225. We're going to get here X, and we're going to get X. Well, now we can write the Ka expression. So the Ka is equal to the concentration of H3O plus divided by the, times the concentration of Cn minus divided by the concentration of HCN. Same as before, products over reactants, we ignore water. In this case, we have the Ka, so we know that, and we know these are each X, and we know that this is 0.0225. So we can plug in what we know. So 4.9 times 10 to the minus 10 equals X times X divided by 0.0225. We need to first cross multiply and put the x's together, and we find that x squared equals 1.1 times 10 to the minus 11. So I just moved the x squared to the other side. To solve this, we simply take the square root of both sides, and we find that x is equal to 3.3 times 10 to the minus 6. And this is a concentration, so it's molar. And specifically, this is the concentration of H3O plus. Now, if in this problem we were asked for the pH, we would simply take the negative log of this, and that would give us the pH. But in this question, we're not asked for the pH. We're asked for a slightly different calculation, which is the percent ionization. Well, the percent ionization as we just discussed a minute ago, is equal to the concentration of H3O plus, make that H a little bit more clear, okay, divided by the concentration of, in this case, HCN times 100, because it's a percentage. We usually multiply those by 100. So when we want to find the percent ionization, we plug in what we know. Well, we know the concentration of H3O plus, that's what we just figured out, 3.3 times 10 to the minus 6. We know the concentration of HCN because that's given to us in the problem, which is 0.0225. And then when we do that math and multiply it by 100, we find that the percent ionization is equal to 0.015%. So the percent ionization here is not very strong, which we wouldn't have expected because, one, HCN is a weak acid because it's not a strong acid, and also the Ka here is a very small number, right? It's 10 to the minus 10, so the percent ionization is very low. Said another way, this solution isn't very acidic. In the next part, what I want to talk about is the relative strength of these acids. So I've shown this slide before, but we talked about it in a little bit of different context because at that point, we hadn't thought about the Ka. Remember that for the Ka, we have products over reactants. Said another way, for the Ka, the products, H3O plus and A minus, the bigger that these numbers are, the more HA dissociates because these are the products of the reaction. So the greater the number on the top, therefore, the greater the Ka. So if we get a lot of H3O plus in solution, we have a stronger acid. And if we look at something which completely dissociates into H3O plus, like HCl, okay, or H3O plus itself, the pKa here, or excuse me, the Ka here is 1, which is a very large Ka. If we look at something that is a weaker acid, like HF, it's 10 to the minus 4. Weaker still, acetic acid, 10 to the minus 8. And weaker even still, water, 10 to the minus 14. So you could see here, as the Ka becomes smaller and smaller values, okay, the strength of the acid is going down. Said another way, the higher the Ka, the stronger the acid. Because pKa is the negative log of the Ka and is really about the exponent, the smaller or lower the pKa, the stronger the acid. So if you're given a table with, 3 different acids on it and it gives you their pKa values, you're going to want to pick the one that's the lowest. If you're asked for which is the strongest acid. And if you're asked for which is the strongest acid and you're given the Ka values, you're going to want to pick the one that's the biggest number. But remember that these are negative exponents. So minus 6, 10 to the minus 6, is a much larger number than 10 to the minus 14. In the next section, we're going to look at KBs, which I'm guessing you could figure out what KB might be. But KBs, okay, are going to work in a similar way. However, they're not exactly the same. But since we haven't talked about KBs before, we're going to do that first. But the general idea still holds true. If the KB is higher, it's a stronger base. If the pKb is lower, it is a stronger base. You'll notice the scales work exactly the same way. Strong bases are on this side and they start at 1 and go to 10 to the minus 14. Strong acids are on this side and they start at 1 and go to 10 to the minus 14. However, since we haven't really talked about KB yet, I think it's a good idea that we use the next section to talk about KB in much more detail.